In this lecture, I am going to deal with the relation between force and potential energy. First, let us define what a conservative force is. Conservative forces are the forces where the work done by them along a path depends only on the endpoints. It is independent of the path taken by the body. So now, if work is being done between 2 points by a conservative force, that work done can be expressed something like this. W is equal to integral RA to RB F bar dot dr bar is equal to, as I said, it depends only on the endpoints, so this should be equal to the function of RB minus function of RA, or I can also express work done. W is equal to minus U of RB minus U of RA, where this function U is called potential energy function. So I can express U of RA minus U of RB is equal to integral RA to RB F bar dot dr bar. Another important point to note is the work done by the conservative force along a closed path. In the sense, integral f bar dot dr bar over a closed path is always equal to 0. With this idea in mind, let me further develop the relation between force and potential energy. Now, imagine some work is done to displace a body through a small value delta r. So this work done can be expressed something like this. W is equal to integral r to r plus delta r f of r dash dr dash is equal to, just with the information we just had it, this can be expressed as u of r plus delta r minus u of r, but with a minus sign here. Or I can express u of r plus delta r minus u of r is equal to minus integral r to r plus delta r f of r dash dr dash. Now the left hand side can be expressed as delta u, the change in the potential energy, is equal to the right hand side, if delta r is very small, can be approximated to f bar dot delta r. So now I can express, but do not forget the minus sign here, minus f bar dot delta r bar. Or I can also express delta u is equal to minus, as force is a vector quantity, fx I cap plus fy j cap plus fz k cap dot delta x I cap plus delta y j cap plus delta z k cap. So delta u can be now expressed as minus fx delta x minus fy delta y minus fz delta z. But then there is an alternative way of answering delta u. Delta u can also be expressed something like this. Delta u is equal to dou u by dou x delta x plus dou u by dou y delta y plus dou u by dou z delta z. Now let me proceed further. Comparing this equation with the above equation, let us call this as 1, call this as equation 2. So now comparing 1 and 2, we can express fx is equal to minus dou u by dou x, and then fy is equal to minus dou u by dou y, fz is equal to minus dou u by dou z. Remember, equation 2 is valid even when delta y and delta z are 0. So, expressing fx, fy, fz, I can express force, which is fx I cap plus fy j cap plus fz k cap, as f bar is equal to, in place of fx, let me substitute this, so that I cap minus dou u by dou x minus j cap dou u by dou y minus k cap dou u by dou z. This is how we can express it. Or, in other words, this can also be expressed as f bar is equal to minus I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z of the potential energy function u. In other sense, f bar is nothing but minus del u. We call this as gradient of potential energy. So, conservative force can be expressed as the negative gradient of potential energy. Remember, delta is called a vector differential operator. Vector differential operator. When del is operated on a scalar function, we always get a vector quantity. F bar is vector quantity. Potential energy U is a scalar function. So, this is the relation between the force and the potential energy. And this is read as force is negative gradient of potential energy. Potential energy. Thank you.